Hello, guys. Today we are back with another topic of physics, and today we are going to be talking about the classical mechanics part of physics, a topic which is very important yet very simple and easy. So, today we have here, as you can see, the headline, which is rigid body. Uh, A rigid body is an idealist body in which the distance between any two points remain constant regardless of any force applied. Suppose we take two points in this rigid body. One of them is J and another is K, and we draw a distance vector in between them, which is RJK vector. What we are going to find out is that this r, the magnitude of this vector always remains constant. You see, it will never change regardless of any forces applied, and that is the primal condition of a rigid body. And rigid bodies can have two kinds of motion primarily. One of them is translational motion, and another one is angular motion. So when we say rigid body, when like suppose it is a this disk is a rigid body and it is going on a surface, it has a velocity of v and it is having a transitional motion on the ground, then we can also have another kind of velocity, which is like this rotational motions that you can see. This rotational motion, which is also known as omega, is the body's movement around its own axis of the center of mass. This is the center of mass, and we can see that it is having a rotational motions like that, and it's called angular velocity. And the motion it has like linearly, it is called translational velocity of the rigid body. And if you try to count the angular velocity or the angular motion of this rigid body, you have to have an absorber which is also moving at the same speed, same transitional velocity as the rigid body, obviously. So when we see that it has the same velocity, which is v center of mass, we will find that it only has one. From the observer's point of view, you will see that it only has one velocity visible, which will be the angular velocity, as both of the objects and the observer are moving at the same translational velocity. And if we consider the center of mass, the reference frame, the center of mass will be at rest, and other particles of the rigid body will have a rotational motion about the axis of the center of mass. We'll find out that sorry for the inconvenience. We'll find out that the torque, which is very similar to force in terms of translational motion, we'll be able to find out the value of torque by taking the moment of inertia from the center of mass and the angular acceleration of the body. And if you try to find out the total energy in this rotational motion, it will be half into the moment of inertia from the center of mass, you know, from the center of mass, and we'll have to multiply it to the square of the angular velocity that it is having. Thus, you'll be able to find the total energy that resides in this system. And after that, have a topic where we'll have to show how we can measure the angular velocity, the angular acceleration. So, firstly, we take a rigid body, see the green disc like body here, which will be moving, which have a displacement of theta, angular displacement, which we know as theta, and also have an acceleration of alpha, which is a function of t. We can see, if we consider a vector here, we can see that the r, which is the radius, if you consider that the x axis and the displacement vector as the y, you see that the k will be the z axis, the k unit vector will be towards the z axis. So firstly, well, what we'll have to find out is the angular acceleration of the body, obviously, which is a function of time t, you can see here, and it will be the double differentiation of theta, which is the angular displacement, and we'll consider a unit vector which obviously would have the magnitude of 1 only. It is more similar if you try to relate it to transitional motion. You find that when you find acceleration in transitional motion, you just double differentiate the distance. You'll find that it is a sorry, it was some inconvenience. You'll find that the double differentiation of the displacement, and we can also have a unit vector. It is optional, but in terms of when you try to only figure out the magnitude of anything, the unit vector is not very necessarily, you could consider scalar. But when in dynamic calculations, you also have to consider the vectors, as it has specific direction, the acceleration of the both angular motion and the transitional motion as well. You see, this equation's pretty similar. You see, if I highlight it with the yellow color, it's pretty similar. You can relate to that. And if you try to find out the angular motion from this angular acceleration, which is omega, which is also obviously a function of t. Why all of these equations are a function of t? Because t can be variable. You see, we can take any time frame for this. Like, it can happen in 10 seconds, it can happen in 15 seconds, anytime. So we consider t as a variable, and as in variable, as we have a variable here, we have to use differential equations and integral equations to figure out the solution. So we have angular velocity, which obviously would be the differentiation of angular displacement, which is also pretty similar what you have studied in transitional motion, which is when you find out the v, the transitional velocity, you just differentiate the displacement with respect to t, and you can have any unit vector. You can take any unit vector, it could be I, j, k. So what we will do is that, and if you try to find out find out the angular velocity from the angular acceleration, should be find out this angular velocity from the angular acceleration. How we can do that is, we know that angular acceleration, if we consider z-axis as we are considering k as our unit vector, would be the differentiation of angular velocity, which would be the double differentiation of angular displacement. And if we try to figure out this out of the total equation, let me make space. You will see that if we try to find that out, we'd have to, if we consider it from this equation, we would have to put it like this. For more better understanding, let me do it like this. It's time 0 to t, you have the angular velocity, and to find it, you have to integrate the angular acceleration with respect to t, and that is the main equation in order to find the angular velocity from angular acceleration. We see that one pattern is that when you go from here to here, you differentiate the equation with respect to t, but when you're going from angular velocity to angular acceleration, you're integrating from limit 0 to t, which is a very important thing to understand. And as you can find, if you calculate this equation, you will find the angular velocity of the rigid body, which is in rotational motion. And if you try to find out the t from here, which is obviously the displacement, again, it is the same analogy that we have used here, as displacement is, as we find angular velocity as the differential equation of displacement with respect to t. In order to find the displacement, we'll have to integrate the angular velocity with limits from 0 to t. Thus, you can see the equation is written here. Why? In order to find the displacement, you are integrating the angular velocity with respect to t, and thus you'll be easily able to find the calculation. This was a small video trying to give you some information on how to find out how to understand the concepts of rigid body and how the motion inside the rigid body works. Hope this video helps, and if you like my video, please subscribe, and see you in the next video. Thanks for today.